We've talked about refraction already, which is one thing that can happen to light when it reaches a boundary between two different media. Light hits that boundary, and assuming that boundary will allow some light to enter it, the light will change speed. It will therefore change wavelength. It will therefore change direction. That's called refraction. But some of the light will reflect off of the boundary. We're not talking about total internal reflection here necessarily. We're talking about just something that happens when light strikes a boundary. Some of it will always reflect. And it obeys what we call the law of reflection that we learned about briefly in Physics 20, which says the angle of incidence as measured from the normal line, as we know what the normal line means because we talked about that with refraction, is always going to be equal to the angle of reflection as measured from the normal line. This is so much easier than refraction. With refraction, we've got to use Snell's law to find an angle that changes because the speed changes and so on. With reflection, it's got a situation like this. A ray of light strikes the boundary at an angle that we call theta 1 or theta I. It's going to reflect off of the boundary. Some of it may go through, but the part that reflects will reflect off such that theta I or theta 1 is going to be equal to theta 2 or theta R. The angle of incidence will be equal to the angle of reflection. That's a lot easier than using an equation like sine theta 1 over sine theta 2, v1 over v2, and so on, right? We don't have any other option for refraction. We have to use Snell's law, but for reflection, it's much, much easier. Theta I equals theta R. Let's take a look at a couple quick examples before we move on from this here. First one, what's the angle of reflection? Easiest question in the world, right? Measured from the normal line here, it's going to be 48 degrees. Boy, let's hope we get a question on an exam that's that easy. Don't make it harder than it has to be if you do happen to get a question that's that easy. All right, next one's a little bit harder. What's the angle of reflection off of the second mirror? Let's assume, we should be told, that the angle between the two mirrors is 90 degrees. Let's figure out what the angle of reflection is off of the second mirror here. Okay, the first one reflects at 55 degrees, like this. And there's going to be a boundary here. Right here, it's going to bounce off like this. What angle does it bounce off of? Well, if that's 55, then this one's got to be 35 degrees. Because 55 plus 35 plus 90 gives me 180. And all the angles inside a triangle have to add up to give you 180. This one's going to be 35 degrees as well. So the angle of reflection off of the first mirror is 55. The angle of reflection off of the second mirror is 35. At some level, we all knew this law of reflection already, right? If you've played pool, you know that when you hit the cue ball off of the bumper of the pool table, it bounces off at the same angle that it struck it at. You know that if you're trying to throw a ball off a wall and get it to somebody else, you know that it's going to reflect off at the same angle that it struck the boundary at, right? We know the angle of incidence equals the angle of reflection. The one thing I'll caution you on is to remember to measure it from the normal line as opposed to from the boundary. All right, let's have a look at a more application of reflection here. This is a plain flat mirror. This is like the bathroom mirror that you see in the morning every time you get up out of bed. You look in that mirror and you see yourself in that mirror, right? You see an image of yourself in that mirror. We learned to draw ray diagrams already for curved lenses. So we learned to see what maybe we'd look like if we looked into a curved lens. What are we going to look like if we look into a plain flat mirror? Well, if you think about it, based on experience, you know that you look pretty much the same as you really are, right? You don't appear to be upside down in a bathroom mirror. You don't appear to be bigger or smaller in a bathroom mirror. You're not projecting the image of yourself onto a screen. You're looking into the mirror in order to see it. Let's take a look at the ray diagram that we would draw for that plain flat mirror and kind of justify those observations that we've made as late as 3 hours ago, 2 hours ago. Here's our object. This could be you. This is the mirror right here. Let's draw 4 rays for this one. 4 rays this time. The first 2 rays are going to come from the top of the object, so they're reflecting off of your head. Okay, let's say this is Mr. Sinclair standing there. The light's hitting his head, and reflecting in all different directions. Two rays are reflecting such that one of them goes like this, perpendicular to the mirror. When it hits perpendicular to the mirror, it's going to bounce straight back. So it's going to go back like this. And hit him in the head again. Another ray of light that's coming from the top of Mr. Sinclair's head is going to go like this. Well, where does it bounce off? Something like this, such that the angle of incidence equals the angle of reflection. Where's the image of Mr. Sinclair's head? Well, they don't intersect here, so let's extend the reflected rays back with dotted lines. The first ray reflected back to the left, let's extend it back to the right. The second ray reflected back down and to the left, let's extend it back up and to the right. So it's going to look something like this. That's where Mr. Sinclair's head is going to appear in the mirror. Let's deal with his feet now. See, he's got nice shiny shoes on. He's reflecting light from the sun, all different directions. The first ray of light reflects off of this nice shiny, you know, those tuxedo shoes that are so incredibly shiny. Oops. Going back here, reflecting off perpendicular to the mirror. It's going to reflect back off of the mirror, straight back like this. But then there's another ray of light that's coming from Mr. Sinclair's shoes that maybe it looks like this. It reflects back like this, so that the angle of incidence equals the angle of reflection. Let's extend the reflected rays back, and that's where his feet appear. So Mr. Sinclair's feet appear here, his head appears here. Lo and behold, look at our image. If we look at the same attributes or characteristics of the image that we looked at for lenses, we would say that this one is same size. Well, that should make sense, right? You look into a mirror, you appear to be the same size as you really are. A plain flat mirror, that is. You don't appear to be bigger or smaller. You're the same size. You're upright. Ever look into a bathroom mirror this morning and see yourself upside down? The only way you're going to be upside down in that mirror is if you're standing on your head. Which I don't know that anybody's ever done that. Stood on their head in the bathroom in the morning looking in the mirror. Probably somebody somewhere has. But in the end, we'd still say it's an upright image because our object, it's the same side as our object is. Real or virtual? It's virtual. Dotted lines intersect. In order to see the image of yourself in the mirror in the morning, you've got to physically look into the mirror in order to see it. Right? You can't project it onto a screen. You ever try to project the image of yourself onto the wall behind you? You can't do it. Hey, we showed you how to project the image of a Canada flag from the whiteboard onto a screen. That's a real image. You can't project the image of you onto a screen when you look into the mirror in the bathroom. It's got to be a virtual image. And we know that because it's dotted lines that intersect. All right, so there's a plain, flat, everyday mirror. Let's look, though, at curved mirrors, much like curved lenses. There's two types. But look at the difference here. Okay, on the page that looked almost exactly like this for the notes that you did on curved lenses, we said a converging lens was a convex lens. A diverging lens was a concave lens. It's the opposite for mirrors. A converging mirror is a concave mirror, or a mirror that's thinner in the middle than it is at the edges. A diverging mirror is a mirror that's convex, or thicker in the middle than it is at the edges. So be really careful about that. Converging means, converging means rays converge, whether we're talking about lenses or mirrors. But rays converge in a lens when it's thicker in the middle. They converge in a mirror when it's thinner in the middle. You can see, this is kind of like a fun house, right? You ever been in a fun house where you see distorted images of yourself? This is a concave or converging mirror where the guy is standing really, really close to it. Look what he sees. he sees this massive image of himself in this concave mirror. Now, that doesn't happen all the time. Depends upon where he's standing, right? If he's standing back a ways, the image that he's going to see is going to look entirely different. Diverging mirrors or convex mirrors, where do you see these things? The last time I saw one, I was in a parkade. Sometimes they have them in parkades because you got to go around corners, and sometimes you can't see cars coming, so it allows you to see around the corner. You used to see them in convenience stores, not so much anymore, but the shopkeeper would be able to look from where he or she was standing behind the counter into this convex or diverging mirror and see the entire store. Now everything's smaller. You can see the image is going to be clearly smaller, virtual, but at least it allowed him or her to see the entire store at once. Now we don't need those, right? Because we have video cameras now. I think they have one at the pool in Okotoks. If you go in the hot tub, there's a big convex mirror or diverging mirror, which allows the lifeguards to see the entire hot tub at once. Now, the downside to it is that everything appears to be smaller than it really is. Oh, speaking of smaller than it really is, where else have you seen a convex mirror? Just thought of this one. In your car mirror, the right side, right? Object and mirror are closer than they appear. It's a slightly convex mirror, which has the downside to make everything appear smaller, right? But the upside to allowing you to see a bigger range, right? A wider swath of things behind you. We're going to draw ray diagrams just like we drew with mirrors. The first one that we're going to draw is for a concave mirror, a caved-in mirror, also known as a converging mirror. We have our principal axis. We have our focal point. We have 2F, same as we had for lenses. We don't have an optical center, though. Okay, the optical center would be a characteristic of the lens, not of the mirror. Let's put our object way out here beyond 2F. Now, there are 3 rays that we can draw for this one. We will only ever draw 2, but unlike lenses, we can't always draw the same 2. So it's a little bit harder than it was for lenses. The first ray, the good news is it's the same as it was for lenses. First ray is going to go from the top of the object parallel to the principal axis. Now for lenses, it would converge down here at a focal point over here, right? But for mirrors, it's going to reflect down through a focal point. If you were to look at a normal line to the mirror here, you would find that this angle of incidence was equal to this angle of reflection. Now, we don't have to go through that process of using the law of reflection every time, but the law of reflection would hold still every time. Now, that's the first ray, parallel down through the focal point, same as it was for lenses. Second ray is a little bit different. Second ray is going to go from the top of the object down through the focal point. Where do you think it's going to reflect? If we go parallel then through the focal point, then where do you think it's going to go if we go parallel first? Through the focal point first. It's going to reflect parallel to the principal axis. So the first ray is parallel down through the focal point. The second ray is going to be through the focal point, and it's going to go parallel. Hey, look, we got 2 rays intersecting here, right? Means we got an image. Image is formed right there. First characteristic, it's smaller than the object is. It's inverted, it's upside down, and it's real. Solid lines intersect. We could project this onto a screen if we want. We'd have to put the screen below the principal axis and at the right spot in order to see it, but we could do that. Now, I told you with 3 rays that you could draw, but you only ever need to draw 2. You get to choose which 2 you draw. The first one is going to always be your first choice. Sometimes you're going to choose the second ray that we just drew. Sometimes you're going to choose a third ray that I'm about to show you right now. For this particular ray diagram, I wouldn't draw the third ray. And I'm just going to show you how that third ray works right now. Okay, if we draw the third ray from the top of the object down through 2F, let's assume that it hits the mirror, it's going to bounce back right through 2F, like this. Where does it intersect? Exactly the same spot, right? So that third ray is going to go through 2F, and then it's going to go back through 2F. Which, by the way, 2F, twice the focal length in a mirror, corresponds to the center of the mirror, the center of curvature of the mirror. So if we were to make that mirror a complete circle, 2F would be at the exact geometric center of the circle. So sometimes we'll call it 2F, sometimes we'll call it the center of curvature, or sometimes we'll just call it the letter C. Any 2 of those rays would have given me those characteristics, right? I would choose to do the first one and the second one, but really you could choose any 2 you want. There's a couple diagrams that we're going to draw later on where you're going to have to pick the first one and the third one as opposed to the first one and the second one. And you'll see that in just a moment here. Okay, let's draw the next one. This time we're going to put our object right here. Now, be careful when you're drawing this one. This one is tricky, really tricky to get exactly what you want. If your template is off ever so slightly, and I'm not professing to have made your template perfect, or if your rays are off ever so slightly, and you may very well be a 0.5 millimeter off with one of your rays as well, okay, then your image isn't going to look quite right. Just bear with me before you draw this. Watch what I draw. Watch what you're supposed to get. And then you can kind of fudge your diagram to look like what it's supposed to look like, all right? So the first ray is going to be parallel to the principal axis, and then it's going to go down through the focal point. The second ray is going to go down through the focal point, and then it's going to go parallel to the principal axis. It's supposed to be directly below 2F there. And mine's pretty close though, right? It's supposed to be exactly below 2F. And if we draw the characteristics or label the characteristics of that, we would find that it's same size as the object is. It's inverted. And it's real. All right, next one. This time our object is going to be in between F and 2F. First ray is going to go from the top of the object to the mirror. Reflects off. Second ray goes down through the focal point. And even if it misses your mirror, we'll pretend it hits the mirror. Reflects back parallel to the principal axis. What do I get here? I get an image that's formed larger than the object is. I get an image that is formed upside down or inverted, and it's real. So think about, we talked about similarities and differences between lenses and mirrors already a little bit. When we had lenses, whenever we had a real image, it was upside down. Whenever we have a real image with a mirror, it's also going to be upside down. So that's one similarity. Real images were formed sometimes when we had a converging lens. Sometimes formed when we have a converging mirror. Real images are formed with a convex lens, but a concave mirror. Real images were formed on the right side of the lens. Real images are formed on the left side of the mirror. So again, we talked about this earlier on about remembering patterns, right? It's okay to remember some patterns, but make sure you know what all the patterns are before you start trying to memorize any of them. Next one. Not so tricky as the one before the last one, but a little bit weird, a little bit different, because we have to draw a different ray. Remember, we've drawn the first two rays so far, parallel, then through the focal point, then parallel. Okay, this time we've got to draw the first ray, which is going to be from the top of the object, parallel to the principal axis, like this, and down through the focal point. The second ray we're going to draw, we can't draw down through the focal point because we're on the focal point. The second ray we're going to draw is as if it's going from the center of curvature, or 2F. So it's coming from this point right here, 2F. Hits the mirror, reflects back upon itself. Whoops. Reflects back upon itself like this. So first ray, same as it was before. Second ray, draw it, take your ruler, draw it as if, take your ruler, line it up like I am right now with the top of the object in 2F, and then draw your ray to the mirror, and then it's going to reflect back upon itself back through 2F. What do you see here? These two rays don't intersect. Let's extend them backwards. Well, they're parallel. They're not going to intersect back here either, right? We get no image. So just like when we had a converging lens, there was no image formed when the object was at the focal point. When we have a converging mirror, there's also no image formed when we're at the focal point. All bets are off with diverging, right? If it's diverging, there is an image formed when you're at the focal point. But for converging, whether you're talking about lens or mirror, for converging, then there's no image formed when you're at the focal point. Remember the picture that we saw when we first introduced this of the guy looking in the funhouse mirror? His face was massive. He was looking into a concave or a converging mirror. Here, we haven't seen that massive face yet, right? We've seen real images. We've seen no image. But the real image that we saw first was smaller and upside down, same size and upside down, bigger but upside down. His face was same was right side up, right? That's what we're going to get here. This time, the guy looking into that mirror is really close to the mirror. He's inside the focal length. The first ray reflects off of top of his head down through the focal point. The second ray we're going to draw again is actually the third ray again. We're drawing it as if it's coming from 2F, or the center of curvature, and then it reflects back upon itself like this. So again, take your ruler, line your ruler up with the top of the object and the 2F point, the center of curvature. Draw your line up towards the mirror like this, and then back away from the mirror right through 2F like this, so that it's one straight line. They don't intersect, so we have to extend them. And when we extend them backwards as dotted lines, this is what we see. We see an image that's formed behind the mirror. Like literally, you look into the mirror and you see the image on the other side of the mirror. You ever walk into a room that has mirrors on one side of the room? I've done this a couple times. Like sometimes it's like a reception hall or something where there's mirrors on one entire wall, or a dance studio, okay, where there's mirrors on one entire side of the room. And you walk in for the first time, and your first thought is, wow, this room is huge, right? It looks like the room is twice the size that it really is until you kind of get your bearings. It's because the image that's formed in the mirror actually is on the other side of the mirror. So it gives you the depth of perception that it's twice the size. They're in a dance studio, there wouldn't be mirrors like this, right? In a dance studio or a reception hall, they'd be plain flat mirrors. But you get the idea of when you get a virtual image that's formed on the other side of the mirror, it literally looks like it's on the other side of the mirror. What are the characteristics of this one? It's larger, it's upright, and it's virtual. In order to see this one, you've got to look into the mirror to see it. You can't put a screen over there and expect to see it. Hey, this is the guy looking into funhouse mirror. It was on the first page of this stuff, right? Back here, right? It's this guy right here. Okay, that's a big mirror. That is a fairly big focal length, and because of that, he's standing really, really close to the mirror. He sees that image that's right side up, bigger, and virtual. Here's what I'd like you to do tonight. I'd like you to take a spoon tonight, preferably a bigger spoon, like a ladle type thing, and look into it. Look into the spoon. Hold the spoon in different places and see what you see. See the image of yourself when you look into that spoon in different places. And watch what happens when you move that spoon so that your object distance is different. Watch what happens when you are beyond twice the focal length or the center of curvature of that spoon. Moving it closer, moving it closer, moving it closer, your image disappears. And then all of a sudden, when you have that spoon really close to your face, then you all of a sudden appear to be big and right side up. So you're going to see your image is upside down. It gets bigger, 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 and then all of a sudden it disappears, and then all of a sudden it flips over. Try it. Okay? Again, the bigger the spoon, the better. If you try a little, like ice cream spoon, it's too small of a radius really to do it. But if you get a bigger spoon, then it tends to work a little bit better. And it's got to be shiny, obviously, right? Not one of those little green Menchie spoons or something like that. That doesn't work very well. Okay, let's draw the other ray diagrams. Then we'll shut it down, and then you guys can have a chance to work on the homework that I assigned earlier. Good news is that these ones, the diverging mirrors, same as diverging lenses. All 5 ray diagrams are the same. You can probably predict what the characteristics are going to be right now. First one, I'm going to draw the object way out here. Okay, that first ray, only 2 rays that we need to draw, by the way, as well. Parallel to the principal axis, it's going to diverge away from the focal point, like this. The second ray is going to go from the top of the object down towards the focal point. Right? It's as if it's going right to the focal point, except it can't get there because there's a mirror in the way. It's going to reflect back parallel to the principal axis like this. Oops. Let's try that again. There we go. So first ray, parallel away from the focal point. Second ray toward the focal point and reflects parallel to the principal axis. Let's extend them both backwards. Extend this one backwards to the focal point. Extend this one backwards parallel to the principal axis. They're going to converge right here. That's going to give me an image that's smaller. It's upright. And it's virtual. You're going to find when you draw the other 4 ray diagrams for this, you're going to get the exact same characteristics, just like you did with a diverging lens. Same characteristics. And by the way, for the diverging lens, they were all smaller, upright, and virtual. Okay, this is the mirror that you see in the corner store, right? This is the mirror that you see in the parkade or you see at the hot tub at the pool in Okotoks, the rec center, right? Doesn't matter where the object is, the characteristics of the image are all going to be the same.